Hello there, my name is Lindsay Peets and I'm here today to tell you about my scientific research. My project is entitled Controlling Protein Degradation in E. coli through pBAD Promoter Engineering. My research falls under the field of metabolic engineering, which aims to optimize chemical and metabolic pathways inside genetically re-engineered bacterium to synthesize commodity chemicals for society. Inside E. coli, there are different metabolic channels or pipelines that must be turned off in order to divert all energy to the creation of the desired end product. So far, it has been found how to overexpress pathway enzymes, alter regulator levels, and turn off byproduct reactions. The problem arises in how to turn off biomass enzymes, because if this channel is blocked, E. coli will simply die and no product can be formed. A solution to this problem is to control biomass enzyme accumulation through the SSRA-SSPB protein degradation system. This system comprises of two plasmids, the attack and the target. A plasmid is a circular piece of foreign DNA that can be inserted into a host cell in order to alter phenotypic expression of proteins. These two plasmids work together to degrade biomass enzymes through the COPX protease that unwinds and degrades biomass enzymes. To control protein degradation, promoter regions can be used. That is, the DNA region on plasmids that controls transcription inside the cell, which can be changed on the attack plasmid. Previously, the TERK promoter has been used, but it was found to have leaky phenotypic expression, in which it began to degrade biomass enzymes in the growth phase of E. coli rather than the start of the production phase. But the wild-type pBAD promoter has been shown to have a lower basal, which correlates to the least premature phenotypic expression. Therefore, it was hypothesized that if a rhabinose-inducible wild-type pBAD promoter and IPTG-inducible TERK promoter are integrated into attack plasmids, then the wild-type pBAD promoter will dynamically degrade growth and production phases more effectively than the TERK promoter. Biomass enzymes were tagged with fluorescent red protein called mCherry in order to monitor the degradation of these enzymes. It was found that the pBAD promoter had no significant inducibility capabilities of mCherry versus IPTG-inducible TERK promoter. When pBAD attack plasmid were induced with nothing between 135 and 150 minutes, fluorescent biomass enzymes were degraded no more quickly than when induced with the rhabinose, or IPTG, as observed by the amount of fluorescence over optical density before and after induction. This trend also occurred when TERK promoter was induced with nothing. Although my hypothesis was refuted, another interesting trend occurred. No matter when the TERK promoter and pBAD promoter attack plasmids were induced with, more fluorescent biomass enzymes were degraded overall by pBAD promoter attack plasmids versus TERK promoter plasmids at 255 minutes. Ultimately, this research is only one piece in the overall larger goal of creating E. coli that can produce a chemical needed for the production of biofuel that would otherwise be less cost-effective and more harmful to the environment.